Improved load following in a unilateral market with STATCOM SMES. Abstract. This paper presents the advantages of integrating static synchronous compensator, STATCOM, and supermagnetic energy storage, SMES, for load following in a deregulated power system under a unilateral market. Load following, LF, is an essential ancillary service that regulates the generation output power to meet the fluctuating load demand. In a deregulated power system, the network lines may not deliver the contracted power efficiently between generation companies, GENCOs, and the distribution companies, DISCOs, due to line congestion or short-term loss of line or generation leading to a spike in load demand. STATCOM SMES combination alleviate both the congestion and the short-term rise in load demand, improving small signal stability and power transfer capability. A sample two-area deregulated power system has been presented in the paper with linear first-order model of STATCOM SMES for LF. The integral controller gains of both the areas have been derived to minimize quadratic performance index using genetic algorithm, GA. The simulation results obtained from MATLAB/SIMULINK show satisfactory improvement in the peak overshoots and settling times when compared to those without STATCOM SMES combination. Keywords: unilateral market, load following, STATCOM, SMES. Introduction. Lately, the electrical power system has been shifting their operation from a conventional regulated structure to a deregulated structure. The vertically integrated power system, where a single utility managed and operated generation, transmission, and distribution has been unbundled. The private players have been encouraged to organize GENCOs, DISCOs, transmission companies, TRANSCOs, and independent system operators, ISOs, as separate entities. 1. The consumers have the option to choose economical services from multiple GENCOs, DISCOs, and TRANSCOs. Thus, the private players have been forced to manage the entities economically and lay down tariff policies suitable for consumers. In conventional power system, the load demand in a control area is satisfied by the generating unit in the same control area. However, in a deregulated power system, a DISCO can contract load demand from one or more GENCOs in same or different control areas. In a control area, a controller commands the GENCOs to commit to the generation based on the load demand contracts such as unilateral contract, bilateral contract, or contract violation, between GENCOs and DISCOs too. The control command is derived by an error signal known as area control error, ACE. Many heuristic algorithms have been implemented to optimize the controller gains in the literature. A Weyl optimization-based proportional integral, pi, controller has been presented in 3. A cascaded tilt integral, TI, tilt integral derivative, TID, controller to regulate frequency using water cycle algorithm, WCA, has been implemented in 4. A multi-area multi-source automatic generation control, AGC, considering modified virus colony search, MVCS, has been presented in 5. However, the control of a deregulated power system incorporating STATCOM SMES has not been attempted in the literature. The key operational concern in the deregulated power system has been delivering the contracted load between GENCOs and DISCOs. The contracted power has to be within the transfer limit of the network transmission lines. The sudden load demand, line outages, or short-period generation loss causes the transmission line to operate beyond the transmission limit 6. As the transmission line operate beyond the rated limits, the line losses increase and may lead to cascade line failure. 7. The ancillary services such as load following, to track sudden load demand, reactive power support, to enhance transmission line transfer limit, have been crucial to operate deregulated power system efficiently. Maintaining frequency constant is important to interchange the power among the control areas as well as for constant speed applications. The load demand and power generation balance are maintained in the system to limit frequency within stable limit. The power generating units regulate the output power to meet fluctuating load demand through load following 8. Traditionally, power plants with high ramp rates such as gas turbine power plants, fuel cell power plants, hydroelectric power plants, pressurized water reactor, nuclear power plant, etc. have been performing LF, as they can adjust the power output quickly. 912. Recently, semiconductor-based power converters have been developed for custom energy storages such as SMES, battery energy storage, BESS, plugged-in electrical vehicles, etc. for faster load leveling applications. 13, 14. The loading capacity of the transmission lines is constrained by thermal limits, dielectric limits, and stability limits. 15. The stability limitations on the transmission lines have been overcome by FACS devices, and the conclusive limitation on the loading capacity are the thermal limit and dielectric limits. FACS devices enable flexible control of power flow, thereby increasing line loading capacity and minimize line congestion. In addition to the above advantages, STATCOM has been reported to damp power oscillations and improve bus voltage stability. 16, 17. Considering the advantages of the STATCOM SMES stated above, this paper has investigated the benefit of integrating STATCOM SMES in a sample 2-area deregulated system for LF in a unilateral contract scenario. An integral controller has been implemented for the controlling ACE. The gains of the integral controller have been searched to optimize quadratic performance index using genetic algorithm, GA. The linearized first-order model of SMES for LF has been presented in Section 2. In Section 3, linearized STATCOM model has been derived to regulate tie line power deviations. The detailed 2-area deregulated power system, along with the unilateral contract description, has been given in Section 4. The optimization of quadratic performance index, i.e., integral square error, ISE, using GA has been presented in Section V. Section 6 presents the simulation results using MATLAB/SIMULINK, and the paper is concluded in Section 7. Smes Modeling. SMES is an electromagnetic energy storage device. It has a lossless superconducting coil through which DC current flows. The energy is stored in the magnetic field created by the DC current 18. The current through the coil does not vary instantaneously as the coil is inductive in nature. 15. An electronic converter controls the voltage across the coil such that power is absorbed from the grid or injected into the grid as shown in Fig. 1. The incremental current through the SMES coil is given as STATCOM Modeling. Before you begin to format your paper, first write and save. STATCOM is a shunt-connected voltage source converter, VSC, based FACS device that regulates the output capacitive or inductive current independent of the grid voltages. 20. With the frequency deviation as auxiliary control input, STATCOM has been used for power oscillation damping. 21. STATCOM acts a capacitor to reduce the congestion in the transmission line when load demand increases. However, when the load demand drops, STATCOM 2-area model with STATCOM SMES. The deregulated 2-area power system model analyzed for LF is shown in Fig. 5. The control areas consist of 2 reheat generating units each. A generation rate constraint, GRC, nonlinearity of 10% per min 22 has been considered for each of the units. A STATCOM SMES combination has been implemented in Area 1. The linearized state space equation for the deregulated system is given as where A, B and R matrices of appropriate dimensions and X, U, and P are as given below. Each GENCO can participate in meeting the load demand from DISCO based on an agreed upon contract which can be visualized as DISCO participation matrix 23 as shown below. Where contract participation factor, Fij, is the fraction of the total load from JTH DISCO to ith GENCO. The number of rows in DPM correspond to the number of GENCOs and the number of columns in DPM is equal to the number of DISCOs. Sum of all the entries in a column in this matrix are unity. In our case, since there are 4 GENCOs and DISCOs, M equals 4 and N equals 4, the DPM is a 4AA4 matrix. Genetic algorithm. The optimization algorithm search for the best solution in the search space and compare the fitness of each solution until a satisfactory solution is obtained. 24. Genetic algorithm, GA, 25 is an evolutionary algorithm which has been implemented for various applications. 26. The GA algorithm begins with initializing a random population. The population is encoded as chromosomes. The chromosomes are tested for the minimum value of the cost function based on which the selection procedure takes place. 27. The selected chromosomes produce the next generation solutions by crossover and mutation, and this process continues until the best values of Ki1 and Ki2 are achieved, for which the cost function value lies between the confidence band before reaching the maximum number of iterations. It may be noted that W1, W2, and W3 are appropriate weights assigned to frequency deviations and tie line power deviations respectively. In this work, equal weights have been assigned for F1, F2, and PTIE12 since these deviations should go to zero as quickly as possible, and hence the normalized weight gains are unity each. The genetic algorithm parameter values used are given in Table 2. The optimized integral gains, Ki1, Ki2, without and with STATCOM SMES combination in Area 1 for different area participation factor combinations, APF, are presented in Table 3. It may be observed that the optimal gain settings with STATCOM SMES are higher than those without STATCOM SMES. The cost function values against the number of generations with and without STATCOM SMES is shown in Fig 4. Simulation results. The two-area deregulated power system is simulated using MATLAB/SIMULINK with RK4 method. Fig 6 and 7 depict the deviations in area frequencies. It is evident that, with the STATCOM SMES combination, the frequency deviations are damped out faster and with reduced peak overshoots and undershoots. At steady state PTIE12, actual equals PTIE12, schedule, since discos in an area demand power from GENCOs in the same area only. Hence, from 9, tie line schedule power PTIE12, schedule equals 0. Conclusion. This paper has investigated the advantages of the linearized model of STATCOM SMES combination in a deregulated power system for unilateral contract. A STATCOM has been used to improve the line loadability of the tie line, while an SMES compensates sudden load demands, thereby improving the LF. The simulation results show that, with STATCOM and SMES, the peak drop in frequency deviation has been minimized. Also, the tie line power oscillations damping has been improved. This paper has considered only unilateral contract transactions in a deregulated power system, while contracts such as bilateral contract and contract violation needs to be investigated further.